We are back again. I hope we had a good discussion and a good break. And without dis without discussion, actually, it's hard to understand also. So please feel free to ask questions. It actually enriches the lecture, and it helps us in both ways. I also get to see new perspectives, and you also get to learn few things. So anyway, this is where we had stopped before the break, and we saw where the problem arises in this artificial pancreas. We had addressed the first delay or the error that can happen, which is the physiological delay. Now this physiological delay, it varies from patient to patient, or it may vary slightly from individual to individual. Uh, just wanted to recap this technology stack again, where you have in the first technology stack you have the sensors, in the second stack you have the electronics. So first stack sensors, second electronics, third you have the AI models deployed on the edge device, and finally for data storage and cloud, you have cloud for data storage. So these are the four technology stacks that are needed uh, if you are actually planning to develop an intelligent biosensor. And you can work at different levels. Some people prefer to work at stack 1, so they are more into sensor development. So this is mostly electrochemists or chemical engineers. They are more into developing materials, different fabrication methods. Now, not all the fabrication methods, microfabrication methods, are implemented or scalable for manufacturing. So some people look into that. Some people are more into electronics. They make chip designs, integrated circuit design, very low power devices, low noise devices, and some are into the stack 3 purely AI. But generally, whoever I have seen in the domain of biosensors, they work at least in two domains, two technology stacks, either 2 3 or 1 2. So and finally the cloud computing, where it is mainly it is used for data storage and model training if required. So shall we proceed, or we have any more questions?
I think the question was the device, the cesium device that we were looking at.
Yeah.
So, if let's say two-person is wearing the similar cesium devices,
Yes.
can it can both be scanned using a single reader?
uh, that we haven't tried yet. uh, In theory, yes, because we have a single reader in our lab and we have tried with multiple sensors. So I don't know whether you can be able, it is possible to do it simultaneously or not, but at different times you can do, yes,
Different as in like one by one after another.
you can do it, not a
Okay,
problem.
so I mean, I think that is something we have to maybe take care when we productize this.
Yes, so this actually is not something which we have made in the lab. The reader is actually, so as I told you, the sensor which I have shown you is the Abbott Freestyle Libre sensor.
Okay.
So their model is that you actually have multiple sensors. So the sensor is recurring cost, and the reader is a one-time thing that you buy. Okay, so that is their approach, the business kind of.
And the data, imagine I'm using the same reader to read the data from two different sensors.
Yes.
So will it be counted for one patient or same?
So the way to look at the so for example, if you want to look at the Abbott Freestyle Libre sensor data, there is a package, there is a software called Tidepool. So while uploading in Tidepool, you can log in under different names and upload it. So the Tidepool will upload actually 8 hours worth of data. So how you segment that data? If you are aware that at this time I took this person's data and this time I took this person's data, you can segment it. So it's possible.
But that's not automatically provided
No, that's
by
not
these
automatically provided.
readers. Okay, all right, thank you.
Right. So so this just, I think you have seen these devices already in the class. So microneedles, this is the high, magnified image of the microneedle that you may have felt using, or you may have touched it. So this is how it looks like. So the microneedle that you have actually, this is actually gold coated. This microneedle is I think carbon coated, uh, if I remember correctly. So these are the fine microneedle structures that you can see here, and they can actually be used to penetrate the skin and monitor analytes from the interstitial fluid. Okay. So now that we all, so generally this kind of device we have made for low density monitoring, and these microneedle are there for high density monitoring. High density means spatial density. So this is how actually it looks like. Overall, the system looks like this: a closed loop diabetes management platform, where you have the patient type 1 or type 2 BD. They might be wearing a sensor, and the sensor data actually goes into an app. So here we have shown Bluetooth, but about Freestyle Libre, as you all know, they work on the NFC communication. So Bluetooth is more of a continuous. For NFC you have to repeatedly scan, you have to scan the sensor. So once it goes inside the app, from there it actually goes to the cloud. So the AI model can either sit over here, the trained AI model, or it can also run in the cloud. For security issues, generally people prefer to keep it in the ideal scenario is where you are training and forecasting in the app itself, because it's more secure. You don't have to send the data. Uh, but still we have to think of limitations of space, computing power and all these things. So here you can actually you have the cloud for data storage, and over here you can also do forecasting. So there are two types of applications that AI is being used here in closed loop diabetes management. First is the forecasting, and then using this forecast also you can do the bolus and basal dose estimation. Okay. So this forecasting actually requires, although it seems very simple that okay you are following a certain trend, but this glucose level can be affected by multiple factors like we discussed earlier, by meal, by physical activity, by circadian rhythm and stress. So all these factors cannot be modeled mathematically in a simple model, so you require a deep learning model to capture all these variations. Similarly, insulin dose, when a person is taking an insulin dose, the response to this insulin dose, the conversion factor, how well the insulin is actually absorbed by the body, this also varies from person to person at a very small level. Okay, so these variations can again be captured by AI models. So traditionally the approach has been that people use one AI model for forecasting, another AI model for insulin dosing. So that's why if you look into the literature, if you look at papers, so you will see papers for insulin dosing only and papers for glucose forecasting only. So they treat both of this separately. Now application wise it is very time consuming and tedious to have two AI models running together and they are syncing them, and it's very difficult. So in recent years people have started looking at the entire application together, so that you have a single AI model which can do both forecasting, and based on this forecasting, whatever forecast you are getting, you are actually using that for insulin dosing as well. Okay. Just to simplify the previous diagram, we have removed the app and the cloud here. Now you can see the image or the diagram or the system in a much more clear manner, clear fashion. So here you have the CGM sensor, and this CGM sensor, so these are the factors which are affecting your glucose level: physical activity, meal, then you have insulin. So primarily the AI models that we have worked on or we have developed, we are actually considering these three factors mostly. So physical activity level, physical activity can be captured in terms of number of steps, altitude covered. There are also other factors like heart rate. So all these activity you can actually capture using your wearable devices. Nowadays we have Fitbit and other wearable devices that can be captured. Then we have the meal information, and then we have insulin. So regarding these two, so this is done automatically. This is automated because you can use the API of the wearable device to pull the data from this and incorporate it into your system. But about meal and insulin, most of the time patients have to manually declare it. So if they are using the currently available artificial pancreas, they have to manually declare it, that okay I am going to do exercise in the next 1 hour, or even or let's say somebody has taken some meal, they have to declare that okay I have taken meal of this much carbohydrate content. So all of this thing, there is a bit of manual uh, intervention, it's not completely automated. So similarly that's why in technical terminology there are two types of artificial pancreas. So one is called as the hybrid artificial pancreas. Hybrid means there is little bit of human intervention required. The patient has to declare meal, the patient has to declare the physical activity in some cases, and in some cases they also have to declare the insulin as well, although insulin is being automatically given. So these most of the systems nowadays, they are actually hybrid artificial pancreas. The goal is to go for complete closed loop, so where the patient doesn't have to declare anything, everything happens automatically. Okay. So the dream is yet to be achieved. People have tried to do it in many different ways, but it is yet to be done. So here over here if you look at this system, so there is a now let's see why forecasting is needed. Okay. Forecasting is needed because all of us, depending upon person to person, patient to patient, the physiological delay may vary slightly. Okay. Now, generally, if you are an electronics engineer, you are quite used to high frequencies, right? Kilohertz, signals changing within milliseconds or microseconds, but that doesn't happen in the body. If you look into glucose level it takes minutes to change. It's a very slow changing glucose level. So if you have delay, if you are, even if you, let's say if you are giving insulin, then depending upon the type of insulin that you are giving, maybe it is fast acting, slow acting, this actually also affects, it's not in a matter of seconds but in a matter of minutes. So that is why you have to actually forecast the glucose level in advance to preempt the physiological delay and ensure that the forecast is correct, because based on this forecast insulin dose will be given, and based on the insulin dose glucose control happens. Okay. So these are the typical time series forecasting methods that people have used in AI. So recurrent neural networks, LSTM, GRU, and in a very recent network that has come out is called as the neural basis expansion network. Okay, neural basis expansion network. So there are some other advances to this as well. So the advantage here in n-bits is that this actually is interpretable to certain extent. Okay, interpretable. Now there are some, of course, where to use LSTM and GRU. If we had a little bit more time, we could have discussed more in detail. But there are pros and cons of both using LSTM and GRU, and similarly, there are also pros and cons of using n-bits. Okay, both of this actually they require enhancement. Some additional work is required. So initially, when we look like our lab, we started working in the domain of glucose forecasting. So we wanted to see how well this forecasting, how it works, what is different from the Indian in the scenario that we have in India. How is it different from abroad? So if you work in this domain of glucose forecasting, you require data obviously, and data you can get of, there are two types of data. So one is the most popular one. So nowadays there are a lot of data available. So this one actually, this is called as the Ohio type 1 diabetes data set. So this data set actually it has there are two series of data set. One is in 2018 and the other one is in 2020. Now 2018 and 2020 they have used different models of the sensor, and in 2018 I think they capture some more information in the 2020 version uh, compared to the 2018 version. So overall you have around so in this one you have 10 to 12 individuals in both the data sets. So very less, but yet it is enough for glucose forecasting. So here you can see over here, this is they are using actually the 8 device, automated insulin delivery. So this pump 630G is an insulin pump, and then they use different sorts of sensors. This Empatica is a wearable band, like we have Fitbit, we have Google, different bands for monitoring physical activity. So Empatica is a much more advanced band which not only gives your heart rate, and nowadays you have these Whoop that people are using, right, for physical act. So you can actually use it for measuring stress also, Empatica. So different actually bands are there and different sorts of individuals are there, but you see more or less the age is between 20 to 40, and the data set is also balanced. If you look at the gender, then it's more or less balanced. So it's a good data set to start with. Now and anyway, getting data sets where you have closed loop diabetes, people are using like insulin delivery as well as sensor at the same time. It's very rare. So that's why Ohio T1 diabetes dataset is quite popular for people who work in this field, because it has sensor as well as automated insulin delivery or pump based dataset. So this is how the data looks like. You have mostly we are interested in this CGM. So this is your basal rate that I told you about, basal insulin and bolus insulin, and this one actually there are certain. So this is mostly physiological data. You have acceleration, steps, and all this to measure your physical activity, and you also have insulin information. So this is actually insulin information, bolus events. So you can see bolus events whenever a patient is taking insulin. So these are all bolus events, and there are also meal events whenever person has taken meal. So these are all meal events. So these are meal events. and this is bolus, bolus insulin. So as you can see, bolus insulin is discrete because it is taken. So this is so if you look at this x-axis, how many days does it show? It's for 1 day. It's for 1 day. So within 1 day, you can see here, person is taking 3 meals. So these are the meal events, 1, 2, and 3, and then they are taking insulin. So what interesting you see here is the insulin and meal, they are actually close to each other, right? So whenever a person is taking a meal, person is also taking insulin. Okay, and basal is continuous. So bolus is discrete, like I told you, and basal is continuous. It's always there in the background. So it's always there in the background. Very small level, always there in the background. Now, as the person is taking meal, they also have to calculate how much bolus dose is required, and they take the bolus dose. Okay. Anyway, so what I want to highlight here is, let's say I want to take this bolus dose over here, then I cannot take this bolus dose. So in order to unless I calculate what will be the dose, what will be the quantity, how many units of insulin required. So in order to calculate that, I need little bit of background. Okay, little bit of background of what was my previous glucose level, and people also have to calculate. There is a manual method of calculation. They also have to calculate something called as CF, conversion factor. So they have to calculate how much insulin is required for their body. So there is a back of the envelope, means rough calculation. If somebody is taking insulin and they are supposed to take bolus, then doctor gives them a rough calculation method, and using that they actually calculate that. So it's based on their weight and other things, but in order to make it more personalized and better control, so actually we need this kind of AI based methods. Not only that, we also try to collect some data. So this is something which we collected here in Odisha, SCV Medical College. We tried to collect up to 12 individuals. So out of these 12 individuals, there are 6 type 1 diabetes patients and 6 type 2 diabetes, and then we also balance in terms of gender and all that. So this was our system. So we use the Abbott Freestyle Libre, but in addition to that, we found out a device which is called as the Bluecon device. So this Bluecon device actually converts the NFC signal into a Bluetooth. So your patient doesn't have to scan all the time. So it's actually continuous all the time. And then we have the physical activity monitoring device also. And currently we are still collecting more and more data. And I wanted to show you some results also. How well this forecast is working. Maybe I'll show you later on. It's not in this slide, but I'll show you later on. Anyway, so but I will show you the forecasting that is done on this data set. Okay, so this is how you have to actually prepare the sensor. So in this over here, you have the Freestyle Libre sensor, and on top of the sensor, this is the Bluecon device. So this Bluecon device converts NFC to Bluetooth. Okay. So it converts NFC to Bluetooth, and then you have to cover it up. You can cover it up, or you can also leave it. The sensor itself is waterproof. Okay, just for the convenience of the patient, we sometimes cover it up, but it's not actually required. And then the patient has to take an image of the meal. Okay, so we also developed some AI models which we are not going to discuss in this class, but using these AI models, actually the AI model will estimate what is the volume of food and calorie content, specifically what is the carbohydrate content, because this carbohydrate content is actually causing the increase in glucose levels. So this is the first network that we developed for forecasting. As I told you, this network actually, in this network we have used a combination of LSTM and GRU cells. Okay, this is one of the earliest network that we developed. These are my inputs: the past CGM level, past insulin, physical activity, and also meal that the patients are taking. And here we have actually used this WD net. We call it WD net because we have gone for a very wide deep approach. Wide deep means not all inputs are going through the same number of layers. Okay, so there are certain inputs which require more processing, so they go through more number of layers, and there are certain inputs they go through less number of layers. So using this, actually you can forecast the glucose level in advance, because this forecast will again be used for insulin dosing. So you are not, just what we are discussing just beforehand, we are not doing the insulin dosing based on the current level, but on the forecasted level. So this work is actually published. So what are the metrics, how we actually judge whether the forecast is good or not? So these are typical AI metrics, root mean squared error, mean absolute error, but this is something which is specific to glucose sensors. It's called as mean absolute relative difference. Okay. So anyone who is working in glucose sensing or any type of sensor, they use this MARD, mean absolute relative difference. This is the industry sort of metric that is used. In this one, they want to actually using this MARD, they construct something called as the Clark grid error. So I will show you this also, Clark grid error. So this MARD, ideally, if you want to use it, if you want to commercialize your sensor or your AI model, this MARD should be less than 10%. So that is the ballpark figure.
Sir, I had question
Please,
on,
yeah.
I think on the previous slide. Can you please?
Yep.
No, so you said you had some model which kind of calculated the carbohydrates out of the food.
Yes. Yeah.
So which data set that we use to train that?
That is actually we had. So there are some food-based data sets from abroad, from Switzerland we got, from Indian food data set also we have, and we also curated some of our own data sets that there. So from that AI model will actually do mostly your CHO calculation. So in that data set we have actually have different types of food, and from the container you can actually estimate what is the volume of the food, and then what is the calorie content. So how much carbohydrate is there, protein is there, and all these things. So there is a data set. Yeah.
But for example, Indian foods, if we take the example of bread,
Yeah.
there are several constituents of that, right?
True.
And if it's made of different constituent, from the image we cannot detect that, okay,
Yes,
it's made up of that. So
absolutely. So for that, because we did this trial in Odisha, so mostly I also said that we curated some of our own data set, because in Odisha we have a specific way of making foods.
And
So based on that we have made
and
that.
is that data set public or?
No, we haven't made it public,
Okay.
but
Thank
we
you.
can share it with you. No worries.
Sure.
While sharing the slides, I can add.
Sure. Thank you.
Right. So there is a reason why we haven't made it public, because we are still validating it clinically. So once the validation work is complete, then we intend to make it available publicly, because our clinical testing is still going on. So we have tested it in a small number of patients. Like I have this data set that I have shown you. It's only 12, right? 6 type 1D and 6 type 2D. But we want a bigger number. So still we are collecting data on this. So this is the Clark grid error, which is based on the MARD, and in this Clark grid error, basically you have on the x-axis the reference blood glucose level, and then you have the measured blood glucose level. So this glucose level is measured by the sensor. So ideally you want, so what is the ideal scenario in this Clark grid error? Where do you want your sensor to be? An ideal sensor will be where? Straight line, right? So this is your ideal sensor response, straight line. So whatever, let's say if it is 100 here, it should be 100 there as well. Okay, but in real life it doesn't happen. So that's why you have these different areas. Closer to the straight line, the more preferable it is. So that's why we have different areas A, B, and C. So A stands for clinically accurate, B for benign errors but still clinically acceptable, and C for overcorrection. C is also acceptable, but when you are submitting this data to any regulatory agency, they look at what percentage of points you have in D and E. So that will decide whether your device can be used or your sensor can be used or not. Okay. So ideally you want 90% of your points to be within A, B, and C, not beyond that. So these are the forecasting results. So this is again here where you can see here. So there are two plots here. One is the actual data point, and then the black one is the predicted data point. So if you look closely, there is a slight delay between the. So this is due to the model making calculations to do the predictions. So there is another delay here. So one delay is that you try to forecast to avoid the physiological delay, but again when your model is making these predictions, of course it requires some time to compute, and that's where you are actually having some delay as well. So ideally you want to reduce this delay. So if you look at this, if you look closely, then this particular model where you are using only LSTM and GRU or a combination of both, you want to, we have two issues I will say here. So the first issue is that of the delay between the real and the forecasted level. So we want to reduce the forecasting delay. So this is the forecasting delay, and if you look closely, then the model is not performing very well when it is actually very low or very high. So in the peaks, okay. So ideally you want to match these two. So this was the motivation for looking at other time series forecasting methods, okay. Anyway, so you there are three prediction horizons. One is 15 minutes, 30 minutes and 1 hour. So 15 minutes is the minimum forecast that you need to avoid the physiological delay. You can expand your forecast to 30 minutes and 1 hour to incorporate glucose dynamics. So if somebody is taking insulin or the glucose level, if somebody has taken food, it's not going to change instantly, it's going to change very slowly. So this change, that's why when you do go for a fasting blood glucose, or if you go for something called as GTT, does anyone know what is GTT? Glucose tolerance test. So glucose tolerance test is also done to estimate whether a person has diabetes or not. So they give you a fixed amount of glucose and they measure your glucose spot measurement 1 hour and 2 hours. So it is expected that after 2 hours you will have normal glucose level. So glucose is completely maintained. So the glucose homeostasis takes up to 1-2 hours to. So that's why you have forecast up to 1 hour as well to incorporate that physiological aspect as well. Okay, right. So these are the real figures here over here. So you can see that what I wanted to show you is the physiological delay, but here you can see the MARD is still high for 60-minute prediction horizon. It's not less than 10%. It's very hard to achieve less than 10% for 1 hour prediction horizon. Most of the papers that I have seen, they are still close to 15% MARD for 1 hour prediction. Anyway, so we have tested in different clinical data sets. So this is how the Clark grid error looks like. So this is how the typical you ideally you want all your points to be in A, B and C, but as you increase the prediction horizon, you end up having some points in the dangerous region, which is E and D and E. Okay, so this is what is also acceptable to some point. So like I told you, up to 90% of points in A, B and C is still okay. You will never get all the points in A, B and C. So you will always end up with some points in C and D. So but these are like outliers you have. Yes, so this is something which is interesting. So this specific model we actually evaluated let's say you are training. So should we train your model once and keep on using it, or should you update it on a regular basis? So here this plot actually shows that if you go for a personalized approach or a regular update approach, your MARD actually keeps on reducing, or you are able to maintain the MARD well. But if you don't do that, your MARD will eventually increase. So this is actually days. Okay, so each test set is actually 5 days. So like this, test set 1, test set 2, test set 3. So if you update your AI model after 5 days, it performs well. Otherwise, if you don't update, the MARD actually keeps on increasing. Right. So this is the comparison with existing work. So these are all these work. Actually, one more advantage of using, or one more motivation for using this Ohio type 1 diabetes is that if I collect local data, then I may not be able to compare my performance with others, but Ohio type 1 diabetes is a standard data set, like you have MNIST or any other image processing data set where people compare. So like I told you, if you look at there are only few works which have got sorry, this is time lag less than 10%. So here also it's actually 15%, but where we want to reduce is this, the time delay. So as you increase the prediction horizon, so it starts with 5 minutes for a time for a prediction horizon of 15 minutes, the time delay, the forecasting time delay is 5 minutes, but as you go on from 15 to 30 to 60, the time delay actually increases. So ideally you want this to be less and less and less. Okay, so that is the reason behind forecasting framework 2. So in this forecasting framework 2, we use something called as NBITS, neural basis expansion network. So neural basis expansion network was actually proposed by one of the pioneers of AI, Yoshia Bengio, long time back, not long time back, around 2018, 2019. Or even later, I think, I exactly cannot remember. So it was a univariate forecasting model. That means you can only forecast one point, or you can take only one input and forecast one point, and it looks like this. without the attention layer, it had two fully connected layers. Okay, in order to enhance the MARD, let's say we are using this for glucose forecasting, we want the forecast to be as accurate as possible or as close as possible to the actual one. We started using multi-head attention layer. So this is where we did some changes from our own side, where we actually incorporate this multi-head attention, and then we developed this backcast and forecast. Okay, so the backcast is like a feedback which goes back into the model, and then it processes the backcast. So along with other inputs, you have the backcast as well, and then it makes the final forecast based on backcast as well as the current data. Uh, so in this way, actually, you can actually develop. This we call it as. So this is the original paper. So around 2019, which introduced n bits, univariate n bits with fully connected layer, but you can enhance the performance of this univariate layer. You can make it multivariate. You can also introduce multi-head attention, and you can make some nice changes to this, so that your forecasting becomes much better. And here you can also add interpretability. So let's have a look at how you can add interpretability over here. So interpretability means if I am getting a certain glucose forecast, you can answer why you are getting this. Okay. So this particular network actually has enhanced interpretability. That means I'll show you how we do this interpretability. Then it has very less prediction lag because of the backcast. The prediction lag is fast. The calculation is not that difficult, and the prediction lag is less. So if you remember in the previous network for the 60 minutes prediction horizon, the lag was 40 minutes. So we can have a look, and the attention layer actually enhances some performance as well, and there are many other advantages. So if you look at this point here, so if you look at the same data set, Ohio clinical data set, 60 minutes, MARD is around 12.84. We will come to the lag later on. So overall we observed that for the performance is less than 10%, the MARD is less than 10% for a prediction horizon of 30 minutes. Okay. So this is how the plot looks like. It's performance. It is actually in previous plots. If you notice, it was not doing well in the peaks. Now using this new network, the framework 2, actually it works well in the peaks and as well as in when it goes down as well. And it's true for all prediction horizons, whether it is 5 minutes or 30 minutes or it is 60 minutes. Okay. So this difference is still, there is some lag there, but we can see how much the lag is. Okay. And this is the Clark grid error. So most of the points are in A, B and C. Even for 60 minutes, if you remember, there were some points over here in D and E for the previous network, but here you don't observe any points in D and E. Okay. It's the same individual, same person. Right. Now coming to the crux where we really see the advantage. So from 40 minutes, we brought it down to 15 minutes. So prediction lag actually reduces massively. Okay. And this actually helps a lot when you are using it in real time, when a person is using it in real time. And up to now, if you look at the previous work also, it's better than previous work so far. Right. Coming to the more important aspect, which is the interpretability. Interpretability in time series forecasting is actually done. We have seen interpretability in AI models, in images. So it generates some sort of a feature map, and it tells you which, let's say in genomics, when you are using genomics for in pathology, so you have different, you get a feature map. So here in time series forecasting, there are actually two ways in which you can implement interpretability. So interpretability actually was, there are two components. One is called as the seasonality, and the other one is called as the trend. Seasonality and trend. So these are two components. So seasonality and trend. So seasonality is more of a long term, long term changes. It captures long term behavior, and trend is more of a short term behavior. Okay. So when you are interpreting a certain forecast, you can look at which one is dominating, whether seasonality is dominating or trend is dominating, and whichever is dominating, that is the reason for your forecast. Okay. So this was first discussed in around 1990. It's a statistical paper here. Journal of Official Statistics by Robert Cleveland. So they first developed this STL approach for looking at population data. So if they see that okay, a certain disease is going up and going down, let's say in winter we have flu, then the seasonality is causing the increase in occurrence of cold or flu. So in this way actually time series data you can actually interpret, you can put interpretability, you can interpret time series forecasting using trend and seasonality. So these are different mathematical parameters. So in this particular model, because of the forecast and backcast, you can introduce this interpretability in the model, and you can look at this plot how interpretability happens actually in the glucose forecast. So if you look at the black line, this is the original data set, and this is the forecasted data set. The blue one is the forecasted. That's why you see a delay between these two. Okay, shifted, slightly shifted version. Now let's say I want to see what is causing this peak, why there is an increase in this peak. So I can break it down into two components, trend and seasonality. So I can say that at this point where I am seeing the peak, it is because of the seasonality component, okay, and the trend is down. And similarly, let's say, so overall in this figure, if I observe closely, I can say that I can see that the glucose level is going down. Okay, it is going down because the seasonality is dominating over the trend. So seasonality is more dominant over the trend. So trend captures short term behavior, seasonality captures long term behavior. Okay, so this is how you can introduce interpretability in time series forecasting. So in this way we can also do the computational cost analysis of the model. So when we talk about computational cost analysis, we actually look into the floating point operations per second. So for example, here if you see, we have looked at different algorithms, and the algorithm that I just recently showed you, which is based on multi-head attention layer, you see that the number of flops or floating point operations per second is around 5.536 into 10 to the power minus 5. So this is actually an acceptable amount of flops. So we do this flops analysis because if we want to actually implement this algorithm in an edge device such as a mobile phone, then we have to actually compare the number of flops that our algorithm consumes and the number of flops that the edge device can handle. So if the number of flops that our algorithm can consume is less than the number of flops that the edge device can handle, in this way we can actually implement the model on the edge device. Otherwise it is not possible to implement. So this particular model has actually an acceptable amount of flops. So compared to previous models that have been shown earlier, you can see that it's slightly less in certain cases. So it is a nice balance between the number of flops that it is using, and it is also able to achieve this balance, achieve this performance with less number of flops compared to previous algorithms. So this work we have already published in our journal, in the form of a journal paper. So in IEEE Journal for Biomedical, Journal of Biomedical and Health Informatics. So if anyone is interested, they can go and look into it in more detail. So continuing on this end, I also wanted to introduce the benefit of this hierarchical interpolation networks. So there is also another application, another model that we are actually looking into. So this is called as the neural hierarchical interpolation networks with self-attention learning. So this is another approach where self-attention learning has been used. So if you look into the model blocks, so we still have the multivariate time series. So in our multivariate time series, we have the past CGM, and then we have the past CHO, which is the carbohydrate content or the meal content, and the past insulin value and past physical activity. So this physical activity can be classified in terms, or it can be quantified in terms of heart rate. It also can be quantified in terms of number of steps, uh, altitude, velocity, and many other features are there. So in the second layer, we have a temporal convolution layer, which actually extracts the time series or time dependent features out of the data set, or it actually is able to extract the interdependencies in a time series. And then we have the max pooling layer, and then we have a self attention layer, and then we have the as we have seen in the previous network, neural basis expansion network, we have a CGM forecast and a CGM backcast. So the CGM backcast is again fed back to actually capture long term memory interdependencies, and then the CGM forecast is actually used. So within this block is actually placed in a series of blocks, block 1, block 2, block 3, block 4, and then all of this is placed inside a stack. So there are multiple stacks that are available. So this architecture is called as neural hierarchical interpolation network with self attention layer. So this is again another interesting time series forecasting network. So before we go into how do we do this time series forecasting, so we can actually have we do this data training split and between test and training, and then we have hyperparameter tuning. It's standard that is there in all machine learning models that we use. So these are some hyperparameters that we consider when we do the training or tuning through the process. So when we compare this, so we have actually tried and implemented this in the Ohio T1D data set. So as you know, there are two Ohio T1D data set. One is the 2018 one, and then we have the 2021. So over there we have actually done forecasting for again the three different standard prediction horizons, 15, 30 and 60 minutes, and then we look at the MARD, which is slightly lower than the previous work, as we will show you very shortly. So this model also, this is, if you look at this plot here, there are three regions in this plot. This plot you have seen earlier as well. So in this region actually you have the hypoglycemia region, this is the normal region, and this is the hyperglycemia region. So this is hyper, this is the hypo, and this is the normal region. So the model is able to predict correctly for all different peaks, whether it is in the normal region or in the hyperglycemia region. It's able to perform well by accurately predicting for all the different regions. And when we go for a longer forecasting horizon, we have a slight time delay. So we'll have a look at it later on. What is the time delay that we encounter for a 60-minute prediction horizon? And if you look at, so as earlier, we have also done this Clark error grid analysis. So this is a standard analysis method to judge the performance of any machine learning model or a sensor for clinical, using clinical data sets. So we have actually here it is shown as a sample. So as you know, in this Clark error grid we have different regions, so A, B, C, D and E. So most of the time we want the points, the forecast. So on the x-axis we have the original or the real concentration that has been recorded, and this is the predicted concentration. So we want the so the ideal plot is a linear plot. So we want the points that we are forecasting to remain within maximum, mostly in the A and B regions and some in the C. So majority of the points we want to be in the A, B and C region. So if you look closely into these plots, so for a prediction horizon of 60, there are some plots which are in C, but there are no plots in D and E, which is a good sign that our model is good for in terms of deployability, clinical deployability, because most of the forecasting points or forecasted points are in the A, B and C region, or A and B region, and few in C region, which is acceptable. And this is the much more detailed analysis of the Clark error grid. So if you look much closer, so you see that for all the patients, so if you look at all the patients in the 2018 data sets and in the 2020 data set, so you see a very small number, which is 4%, 0.04%. It's there in E. Majority of the points are actually in A, B and C, which is a good sign that yes, our model is performing well. So much more detailed analysis here. So if you look at this work here, so over here if you look at this, so in terms of MARD, our model performs quite well compared to previous works. MARD is the parameter which is used to judge the efficiency or the performance of a sensor, or in this case a prediction algorithm. So MARD stands for mean absolute relative difference, just to recall all of you. So over here if you look into the flops also, the number of flops that are being used is better than the previous architecture, which is neural basis expansion networks. Expansion plus multi-head attention. So, this is better than the previous work, and it actually gives us, it's a good sign that it is more towards deployability of edge device. Okay. So, we are moving more and more towards the deployability in edge devices. Okay. So, the reason we want to deploy in edge devices is that it is more secure in terms of data handling. So, we do not have to send patient data to the cloud. So, it is much more secure. There is less chances of being of any data leakage as we send it over the web. Now, this is an interesting aspect that we are coming to. So, we have mostly looked at glucose forecasting in scenarios where there is not much physical activity, there is some physical activity. Now, we wanted to look much more in detail into physical activity. So, physical activity sometimes presents itself as a limitation for type 1 diabetes patients, because they have to declare their physical activity if they are using an insulin pump prior to their physical activity. So, with this because physical activity also leads to changes in glucose levels. So, we will look at how we can use, so this is mostly a patient driven approach. So, we do not want to put the burden on the patient, we want to put or shift this burden towards the machine or the AI models. So, for this reason we also want to do automatic physical activity classification. So, we will look into detail how different kinds of physical activity affects the glucose level or the glucose trajectory, and how we can actually do physical activity classification to enable a much better patient experience. So, as we know, any bodily movement requires use of muscles like household work or any physical activity, walking, running. So, all of this actually leads to, as we use energy, glucose is being used up or is being released into our bloodstream. So glucose changes are happening. So, anyway, doctors also recommend physical activity, daily physical activity for type 2 diabetes patient. It's part of the WHO guidelines, and also when people doctors also recommend this. But also currently physical activity is not included in artificial pancreas systems. So, it has to be declared by the patient, it has to be planned ahead before if a patient is actually using an artificial pancreas system. So, with this actually we want to look into automatic physical activity classification, so that the patient does not have to declare it. They can simply go about in their life without having to worry about whether they have to put these values in an app, or how long they are doing it, and all these things. So, looking into this, there are different kinds of physical activity. So, mostly we divide physical activity broadly into two types. One is called as the aerobic physical activity, which is like walking, running, cycling, or walking up the steps and down. And then we have the anaerobic physical activity or high intensity physical activity, which is you can look at different figures like working out in the gym, lifting weights. So, all of this is part of the anaerobic physical activity. So, why we are treating this aerobic and anaerobic? Because the behavior of glucose in these two are different. So, as we look into the different kinds of physical activity. So, if you go for a short high intense physical activity, then there is more chance of blood glucose being increased, because body needs a very sudden burst of energy. That's why glucose levels increase. But if we go for aerobic activities, or this is mostly anaerobic activity, if you go for aerobic activities, then the glucose levels tend to fall down. So, in anaerobic it goes up, and in aerobic it goes down. So, this differential behavior of glucose for different physical activity actually leads us to explore more in the direction of physical activity classification for different in glucose forecasting. So, you can also have mixed activity as well, which is much more challenging. So, all of this actually it's important to look into how the glucose behaves. So, in a way to actually, if we can classify the different types of physical activity before we feed it into the glucose forecasting algorithm, so that the forecasting accuracy actually improves. So, in order to validate, so we also developed some models to do this automatic physical activity classification. So, in order to validate that, we are actually relying on a very old data set which is called as the HAR data set, or Human Activity Recognition data set, human activity recognition data set. Or so this data set actually was collected with the help of the sensors that are present inside a mobile phone. So it's more close to daily life, like people are actually using this on in their daily life. So we have the accelerometer data, we have the gyro data, and there are different kinds of activity present. Mostly these are mostly aerobic activities. Okay, so we are currently also working on anaerobic classification, but it's a work in progress. So this is aerobic activity. So in order to do this activity classification, we have actually and the sampling rate is of course 100 hertz, not very fast required, because the activity is actually not intense, it's slow. So in this model actually we are using this Badano attention layer. So we are actually using this Badano attention layer with 1D CNN pathways. So and this actually does the physical activity classification. And as you can see here, the during the process of training, the training loss and test loss are actually quite nice. The training curves are nice. So overall within 100 epochs we are able to train the model. And the physical activity classification, so this is a classification model. In this model you can see most of the activities are correctly classified. So it's a very nice model which is useful to use. And here we have the so this is the layering. We have a bidirectional GRU followed by a Badano attention layer, followed by a 1D CNN, followed by an extra trees. So similarly, if you have so this is another model that we are looking into. So all of these are present same, but in the terminal layer we have the XG boost or extreme gradient boosting. So here if you look at the performance of different models, so it's quite as you can see here, this layering actually outperforms all the other different models that are being used. So how now we can see how this particular model performs with in comparison to others. So there's also extreme gradient boosting. So if you look at the random forest also, in terms of so in the UCI hard dataset, so there is also another option that you can use, which is the random forest. So overall, if you plot the metrics, then if you look into the 4 metrics: accuracy, precision, recall, and F1 score. So if you look at these different metrics, uh, the extra trees, which is by using the terminal layer as the extra trees, it actually performs well compared to other layers. So in comparison to existing work, the model actually outperforms in all aspects of accuracy. So all these models are actually using the UCI HAR dataset, as you can see, and this dataset has been used it's a standard dataset, and it's good for comparison, model comparison. So you see that the proposed model actually works quite well in comparison to existing data work. And this work has also been accepted in a journal, which we if you, when you can actually go and read about this also. Okay, so finally we can show you an overall system. So how does an overall complete integrated system looks like? So the integrated system looks like this. In the integrated system we have the CGM, we have the meal input, we have the physical activity, we have insulin also. So the CGM actually autonomously comes through the CGM sensor. The meal information you can extract using a photograph. There is a model which actually converts this photograph into the calories, or the most importantly the carbohydrate intake. So this model we are not looking into much in detail because of shortage of time. Then we have the physical activity classification. This model we have already looked into. Then insulin data is currently being entered manually if a person is on multiple daily injections. So if a person is on insulin pump, then it can be automatically integrated into our system by actually using an API. So all of this information is actually stored in the cloud. It actually, the data goes to the cloud through an app. So there is a patient app which actually sends all this data to the cloud. And the doctor also has there is a doctor app as well. So this is the doctor app. So the doctor actually can monitor the patient individually through their doctor app. Okay, so So doctor has a mobile app as well, and there is a web app as well. So web app is generally used for clinics, and mobile app is generally there for emergency situations where the doctor may need to monitor the data from the patient. And then of course whatever forecasts are there, it is actually sent back to the patient app and as well as to the actuator, and through the patient app to the actuator. So this is the actuator, this is the actuator or the insulin pump. Okay, so in this way the entire system works. So this is a screenshot of the mobile app that we have developed ourselves. So here we have the current glucose level, the last meal information, insulin dosage, the meal time and dose time, and physical activity grading. So depending upon the different types of physical activity that people are doing, whether it is anaerobic, aerobic, what is the intensity of aerobic activity. So there is a physical activity grading that is being done. And over here there are other panels also. So you can look at time series data. If a patient wants to do manual entry of the data, then it can be done here. Then if any updates or to the patient profile, they're also mentioned here. So in order to sync our if let's say a patient is wearing a Fitbit or any physical activity band, so there is also a flow to integrate the physical activity band data automatically uh, through the app. So this process actually shows how using an access token you can actually give permission to the app to extract data from the Fitbit API. So this is the overall you can see the different uh, connections that are from which data is being extracted. So every patient has a patient ID, and every patient will have glucose levels coming in from the sensor. Then you have the CHO level, insulin level, meal times, and insulin dose time. All of this is actually present in the patient app. And then within the profile, there is a profile dashboard. Then you can have the previous report, and this report is actually downloadable. And then there are different charts that can be plotted, and this is actually with the help of the REST API, it can be sent to the front end. Uh, then we have different glucose forecasting models. So all the patient data that is present from the mobile app, we are actually taking in the glucose prediction. So currently we have two models. One is for glucose prediction, and the other one is for insulin dose prediction, and this data is again sent to the model outputs. So this is actually running in the cloud. Currently it's running in the cloud. So so it can be moved later on to the edge device, or you can download a trained model also. So if you have a trained model, a trained model can also be downloaded currently to the edge device. So every time if you want to if you see that the model is not performing well, then a new version of the model can also be downloaded later on. And then we also have the physical activity band from which data is being extracted autonomously and being fed into the physical activity level. So this is the web app. A patient actually can so there are actually different access levels. So one is the doctor level, then one is the patient level. So doctor can see the reports or the profiles of different patients under that particular doctor. Then patient can only see his or her own information. Then we have the technician or the nurse who can actually add a new patient or register a new patient into the system. So finally, we have an overall web app which is running on the Google Cloud platform, which is the first step is to register. Once the patient is registered in the, so this is the doctor web app. So the first step is actually registration of a patient, followed by you can see different patients are present under a single doctor. So and once the patient is registered, the doctor can actually look at the different values or the glucose trajectory and the time series data of the patient. So this is the a doctor, if a user is denoted as a doctor, so they can actually, first we have to do the doctor registration. So this registration is done by the super admin, and once the doctor registration is done, the super admin has to accept the registration, and once the doctor is registered in the system, now the doctor can register new patients under himself or herself. for their in order to monitor them. So all of this actually is made possible through the REST API and using Dockers, um, uh, and using these servers, a Django server and an Nginx container. So all of this actually is deployed. The entire infrastructure here is deployed on Google Cloud, as you can see. So overall it looks like this. So this is the overall system architecture, where we have, let's say, for multiple patients, we have the CGM sensor, we have physical activity band, and all of this is actually going into the Nginx server, and the platform is running a G-Unicorn web server, and there are different model databases. So all of this actually is combined and running, and then we have the Google Fit API, which is extracting data. So this Redis database is actually extracting data from Google Fit API using the API of Google Fit, or if you are using Fitbit. So previously they used to be separate. Now Google has actually acquired Fitbit, so it's all in one big system. So once the model actually is developed locally, so the model is actually packaged, then a Google Cloud storage bucket is created. Then this model is uploaded in a in the storage bucket. Then an AI prediction. So then it can now the model can be deployed on a cloud platform for running. So this is something which we have shown here is the CPU utilization. So this is we stress testing the CPU or uh, the server CPU, actually the server, by using it. So how many maximum users can be offloaded or can use the data at one time. So this shows the CPU utilization rate for 1 hour, and for 10 simultaneous. So there are 10 users who are trying to simultaneously access this. So we are actually using 10%. So overall we can go up to 100 users using the same system simultaneously without much problems. So this is again the data rate. So we want to see if the data rate is actually suffering due to simultaneous access to the server, but it's performing quite nicely. And this is the read and write data rate separately that has been done. So to conclude, so physiological delay is the reason why, between blood glucose level, it's the crux why we have to do glucose forecasting. So because of this physiological delay, we need to do glucose forecasting. So high fidelity glucose forecasting is necessary to prevent hyperglycemia due to delayed insulin dosing, or hypoglycemia due to increased or incorrect insulin dosing. Interpretable glucose forecasting helps in increasing the adaptability of AI. Naturally, it increases trust. The doctors are able to actually understand why the model is giving a certain prediction. So understanding the trend and seasonality component of the glucose trajectory, it helps the doctor understand and actually interpret the model. So this actually increases confidence clinically. So for clinical applications, it actually increases confidence and it leads to greater adaptability. Finally, automatic physical activity detection and classification for aerobic and anaerobic activity can aid in a complete physical closed loop system. So currently the closed loop system is requires the user to declare the physical activity manually. So this will not be there if we are actually using automatic physical activity detection. So with this we conclude the lecture, and I must actually acknowledge my team and my funders as well. And there are references also. These are a lot of papers on this in this domain, so which you can refer and you will have access to this.